Welcome to CO2 Mondays with Trevor. I'm your host, Trevor Matthews, and today I got a special guest with me, a really good friend of mine and a mentor of mine, Andre Patenaude. Andre's been with Emerson well over 30 years and learning everything about refrigeration inside and out. And he taught me so much over the years. And he really is the one who first taught me about CO2. And I've seen him do so many great presentations, and we spent many hours talking about CO2. And I really want you guys to all welcome him here. And if you have any questions, please put it in the chat because he's so friendly. He really wants to help the industry out. And we're going to be talking about high ambient strategies. This is something that is key to understanding CO2 refrigeration. And when you start to understand these different strategies for warmer climates, it's going to be a game changer for you because it's going to be very helpful to pick the right design depending on where you're at in the world. So I'm excited about this conversation. Welcome, Andre. How you doing?
Great, Trevor. Thanks a lot for having me on. I really appreciate it. No, it's great.
Yeah. So why don't we start off and you tell everyone a little bit about your experience at Emerson, as well as your experience with CO2, and so we can get to know you a bit more.
Sure. No, no problem. So been with Emerson this year is my 37th year with Emerson. So started back in 1984 with Emerson on the alco valve side of the business. So that's where I started doing, technical training and sales, did some marketing. And then back in the early 90s, Emerson and Copeland kind of merged into the same office. So that's where I learned to do the Copeland stuff back in the early 90s and continued in the training, sales, marketing, and business development. And always the first 30 years were in Canada. And of course, that's where I met you, working from the Brantford office in Canada. But back in 2014, the company asked me to do business development globally for CO2. So I did that. So I traveled around the world and met with our colleagues around the world and talked about CO2. Started building training programs for CO2 for internal learning, external learning, and did that for about 4 years when CO2 started to become more part of our regular business. And the company kind of transitioned my role at that point into a marketing role in the US. So I was doing US food retail marketing, also with a hand in CO2, of course. And in the last couple of years, Emerson's kind of broken us out into different teams, and I'm part of a solution strategy team now. So I'm kind of considered a solution architect, if you will. We've got special people with special skills or subject matter experts in drives, in controls, in refrigeration, all part of the same team. So I'm part of that team now and spending a lot of my time on CO2 and A2Ls and anything sustainable as far as that goes to kind of support customers. So still involved with CO2 is probably a major portion of what I do, whether that's marketing or supporting customers. It's still CO2.
So when did you first start? Was it 2014 when you started learning about CO2? Was there time before that? Did you know about it, and how did that really take off? And then really, how did you start to learn CO2 yourself?
Yeah, great question. So even leading up to that 2014, of course, in Canada, kind of the beachhead for new technologies, as you well know. Quebec, very entrepreneurial province, probably the most entrepreneurial province in Canada. So a lot of European designs come in and they land in Quebec first. And Quebec OEMs and contractors kind of learn that stuff, then it spreads out to the rest of the country. So because it started in the really 2011, 12, I started learning a little bit about CO2. And because I've been in the refrigeration space and it becomes part of our own portfolio, we've had Scroll since 2009.
Wow.
I helped work with the JTAC in Toronto to build a cascade CO2 unit back in 2011, 2012. So I started to learn a little bit as it went on. And when Emerson was looking for somebody to take on that business development role, they reached out to me and asked me if I'd want to do it. So that's kind of
That was a smart move by them, that's for sure.
Well, I love learning new stuff, and of course CO2, as you very well know, um, you never stop learning.
Yeah.
So that was exciting for me to take on this challenge on a global role and learn as much as I could. And you learn by doing, as you very well know. If I'm creating the programs that I'm going to present, I'm going to learn it because I'm the one creating them, the
Yeah.
artwork, the marketing. So anyway, that's how the CO2 learning was accelerated for me anyway.
Yeah, no, and that's really how I learned it. So Andre was building all these great trainings when I used to work at Emerson, and then just getting involved with the team. There was me, Alain Mongrain, there was quite a few other people where we would just sit and brainstorm and help develop and grow the program. Which I thank you so much, because that really got me into CO2. Because before that, I think the first time I seen CO2 was like maybe 2012, 2013, when I was working at Nealon's, and I was working at a site that had a CO2 pump system, or a secondary system. And I was really excited to have the opportunity to learn about CO2 more. And then back in 2017 or 2018, when I was the lead trainer for Canada, I have an opportunity to train all those technicians. And that's really where I started to learn CO2, is when I was doing the training, just involving
Absolutely.
myself and just learning those little tips and tricks from the technicians that been working on some of the systems, because there's a lot of CO2 systems out there now, and it's something that you need to spend time on, and you got to learn about, and really dive into, because refrigeration is refrigeration, but there's always these different things that you need to learn about, and CO2 is one of those cool things that is new and is going to be here to stay for sure. It's not going anywhere. So
No, you're absolutely right.
yeah,
It's here to stay.
so let's dive into some high ambient strategies. Let's talk about why we have high ambient strategies first,
Sure,
and then let's get into some of the different technologies.
sure. Well, CO2 system, if you understand a CO2 base system, um, then, and as you got pretty much need to walk through the system and understand what's going on. So if I take a few minutes, kind of walk my way through the system, and then we'll get to why high ambient strategies are important. Now, you may think of us, okay, we live in Canada, high ambient strategies may not be that important to us. We'll get back to that. But a CO2 transcritical booster system, it's called a booster system, of course, because your low temperature loads have a set of compressors on them, of course, and they could be semi-hermetic, they could be scrolls, but they're discharging into the medium temperature suction. So because they're discharging into that medium temperature suction, that total heat of rejection from the low temp's got to go somewhere. So the medium temperature compressor takes that load and really boosts it up along with its own medium temp loads to the gas cooler. So all of this total heat of rejection from the low temp side, the medium temp loads, that's two sources of suction gas now for the medium temp compressors. And we'll get to the third in a second. There's actually three. So the compressor medium temp discharge up into the gas cooler. The gas goes through the gas cooler in a day like today, which is snowing out here in Ontario. So you're running subcritical. And when you run subcritical in CO2, you've got saturation conditions. So you've got nice cold gas coming out of that gas cooler. It goes to a pressure reducing valve, which is your high pressure valve. And that high pressure valve, literally, like any expansion valve in an evaporator creates flash gas, right? So the high pressure valve coming out of the gas cooler creates a pressure drop, and you've got flash gas that goes into your flash tank or receiver, but you also have liquid that drops out of the bottom. So that flash tank, that vapor on top of that receiver, even in an HFC system, you've got vapor on top of that liquid. You've got a liquid vapor interface. But with a CO2 system, as the temperatures get warmer, that pressure can get very high. So there's a line that comes off the side of that flash tank that gets directed to medium temperature suction. It's a pressure relief, if you will, and it's controlled by another electronic valve. That bypass valve is continuously trimming the flash tank vapor off the tank to maintain a set pressure in that tank. And let's say it's 40 bar, or what's that, 550 pounds or something like that. Let's say it's 550 pounds it's trying to maintain. So that flash gas or mass flow that's going from the flash tank down into the medium temp suction is another load. So I said we've got low temp compressor discharge, total heat rejection. I've got medium temperature loads, and I've got mass flow from the bypass line, okay? In the wintertime, that bypass mass flow is minimal. So it doesn't add a lot of load to those medium temperature compressors. But as it gets warmer and warmer outside, what happens now, your high pressure valve is creating more flash gas. So you have to bypass more flow to the medium temperature compressors. So now you've got compressors that are cycling on just to manage the bypass load. And in the summertime, you could be bypassing almost 50% of your total system mass flow to get rid of that excessive flash gas in the flash tank. Now think about that. If you've got a 10 compressor rack, you might have up to 5 compressors that are running on a standard booster system just to digest the excessive flash gas in the tank.
That's amazing.
That's where the inefficiencies lie. And when you open up the PSS or other compressor manufacturers software, you can actually see how much mass flow in pounds per hour or kilograms per meter, cubic meters per hour of refrigerant flowing in the bypass line at a high ambient versus low ambient, and you can see it. It's like, wow. So if I've got 5 compressors running just to manage that, it throws up a flag, right? What can we do to reduce that amount of bypass?
Yeah, and that makes sense. So, when did it really take precedent to start coming out with these high ambient strategies then? Because 50%, that is a lot of capacity. That's a lot of energy. Like for the end user, that, you know, I guess in warm climates, that wouldn't really make sense.
Well, great point, because early on, I mean, these CO2 started off in Nordic countries, principally, right? A lot of that technology was done in countries where it's cold. And a basic CO2 system makes a lot of sense. And in Canada, it came to Canada.
Yeah.
And even the systems used today in Canada, for the most part, are a standard booster system, because it can operate, well, take Ontario, for example, 90% of the hours of operation, so 8,760 hours a year, 90% of those hours, you're below 60-degree ambient. But the other 10%, if you live in Ontario, you're going to probably pay peak demand charges. So retailers are now saying, yes, super efficient in the winter, but I've got to manage my peak in the summer. So what can I do to alleviate that? So that's why now, even in cold ambient areas, retailers are going and system designers are going, how can I help my customer reduce that energy in those 100 hours or 200 hours in the summer that could possibly impact their energy costs for the entire next year if they pay peak demand charges.
Wow.
Right? So that's where the inefficiencies lie, is that bypass gas line. How do we manage that more effectively?
Okay,
That's
so
where all these high ambient strategies come from.
so you're saying even in cold climates now, like here in Ontario, Canada, that those end users and designers want to have some sort of high ambient strategy because the cost is so astronomical in those 100, 200, 300 hours.
In those areas where you're paying peak demand charges, correct?
Yeah. Wow.
Correct. So
Excellent.
then they need to weigh the CapEx cost of adding an extra high ambient strategy to their system initially versus the energy penalty.
Mm.
or savings, you know.
Yep.
So that's what needs to be weighed. And a lot of retailers are looking to industry to help them understand, especially you take a large retail that's going to do 100 stores across North America. They've got some in hot, dry ambience. They've got some in cool, wet ambience, and they've got some in right the middle of the state. So all these different areas may require a different strategy based on the regional differences, and
Great.
not only
Yeah.
tied to ambient.
Yeah, no, and that totally makes sense. So let's get into some of these warm ambient strategies, and maybe if you know the process of where the first one started, or which one was the first one to where we are today, in because there's a lot of them out there now. If
Sure,
you want to start, let's start diving into some of these different strategies that you see.
sure. Well, in Canada, what I remember, the first strat wasn't even high ambient. First systems did not even have a drive on the medium temp compressor. So now it's standard, right? The lead
Yeah,
compressor's got a drive. So that's has got nothing to do with high ambient, but it does have to do with energy.
yeah,
So that's one thing. The most common one, the easiest one to apply today as a high ambient strategy is adiabatic gas cooler.
hmm.
Now, adiabatic condensers have been around for many years, but just weren't used that much. But now, when we talk about CO2, the net benefit of an adiabatic gas cooler can be tremendous in a high ambient dry climate. It may be 30% efficient, bring you 30% extra value, but in a wet climate like Seattle, Washington, it may only bring you 3%
Yeah,
value because it's so wet there.
yeah,
So those are the variations. So an adiabatic gas cooler, why is that so great? You can take a standard booster system without any extra complexity. And now you're adding these adiabatic pads. Now, gas cooler manufacturers have these gas coolers that have these pads that run along the sides of them, and they're made of this special material. And typically, when ambient reaches about 72 degrees Fahrenheit, a water solenoid valve starts to trickle water along the top of the pad on both sides. So as this water starts trickling down the outer surface of the pads, the gas cooler's bringing in air from the sides. It hits this cold medium, which is water. It brings the temperature down of the air, and that cooler air now touches the aluminum fins, and the aluminum fins are thinking it's colder than it is, than the ambient really is. So all of a sudden, I've got an ambient, a fin that's sensing a colder temperature, which drops its pressure, drops its temperature in the gas cooler, and tries to keep the CO2 in subcritical mode as long as possible.
So why is that beneficial? Why is that beneficial to keep it in subcritical mode?
Well, because of the energy penalty. So if we go back to the bypass, the inefficiency of having a lot of bypass gas going to the medium temp suction and having to bring on extra medium temp compressors, if we can delay that from happening by having an adiabatic gas cooler and reducing the condensing temperature and keeping it below 87.8 degrees, your pressures are lower. That means your flash gas creation is lower. I have less compressors running because everything's running lower, and I'm saving energy.
Yeah.
That's really the net benefit of doing that. The adiabatic gas cooler is delaying the system from going super critical as long as possible.
It sounds like a very simple technology as well. You you
You're
probably
absolutely
have
right.
to have maybe some, I guess, filters on the water to make sure it doesn't scale up as quickly, depending if you have soft or hard water. But besides that, it doesn't sound like it's a super difficult technology to implement. But the key is depending on where you put that. So if you put it in a wet climate, there's probably not very much benefit to it. But if you put it in a hot, dry climate, you're going to get a lot of benefit from that strategy.
Tremendous benefit. We, when you look at Phoenix, Arizona, for example, the impact there is phenomenal. You would expect that a place like Phoenix, Arizona, you'd be running transcritical all the time. Well, if you don't have an adiabatic gas cooler, you will be running there thousands of hours, a few thousand hours. But if you don't, you hardly ever go into transcriticals because the impact of that water is so great on that dry air that it dramatically reduces that temperature of the air before it touches that aluminum fin. It has a huge impact.
Yeah, that's very important. So now you really need to think, if you're a contractor, if you're a designer, if you're an engineer, where is that technology going, and what strategy should I use? So this is one of the strategies that can be implemented, but you need to make sure that climate zone you're in. So that's really cool.
You're absolutely right. And the other thing too, Trevor, is even though it may sound technically feasible and the least complex strategy to use, do I have water available?
That's a very good point.
Right? How much is the water going to cost me?
Yeah.
How clean is that water? And how often am I going to have to change those adiabatic pads? From a maintenance perspective, it's not put them on and leave them for life. There is a service factor involved in don't quote me exactly, but it's 4 to 5 years. They got to change those pads.
Yeah, which makes sense. I've worked on a lot of evaporator coolers in our cooling systems in Australia, where we'd have to go and change the pads and they're all falling apart, and so I'm sure the technology has came a long way, but once again, that's another cost to the end user. So they would have to put that into their profile, and what's the life cycle of this equipment.
Yeah, it's part of that total cost of ownership calculation, the maintenance and the replacement of those pads. However, from a system complexity perspective, it really simplifies the system. From a technician's perspective, it really is a standard booster system with that adiabatic gas cooler on the roof. So it gives you a lot of value.
So I did have a question pop up here. It says, how many gallons used per ton of water is needed for adiabatic cooling? Cooling towers for chiller loose is 2 gallons per minute per ton. Do you know?
I'm not a gas cooler expert by any means. What I do know is the amount of water required is significantly less from an adiabatic gas cooler than is from an evaporative condenser, because you're only using it only activates the hot water typically at 72 degrees and above. So I mentioned in Ontario, it would be less than 10% of the year.
Yeah.
For example, now in Phoenix, I do have the percentages. We've done a study. We know exactly how many hours it would operate, for example, there. But I did take a look at the Toronto numbers. Toronto weather, for example, would be at 741 hours transcritical a year. If you had an adiabatic gas cooler, it'd be 75 hours.
Wow.
And it would only be sitting at the minimum end of it. So kind of gives you an idea.
Yeah, no, that is great. So we talked about, adiabatic cooling. What's another warm ambient or high ambient strategy that you see?
Well, another one that can actually be added to an adiabatic system is something called parallel compression. Now that can be standalone, or it can be added to an adiabatic. And that's kind of and what parallel compression is for us ref guys that have been working on HFC supermarkets, we've been calling those racks parallel packs for years.
Yeah.
So we get into CO2 and someone says, you're going to put parallel compression. You automatically think, yeah, well, I know the compressors are in parallel, but when we're talking about CO2, parallel compression means an additional suction group. So you've got your low temp suction group, of course, discharging into your medium temp. Now, parallel compression is an additional suction group to the medium temp. And that parallel compressor is discharging into that same gas cooler. So why would we want to do that?
So,
Go ahead.
and we call it parallel compression here in North America, but I believe in Europe they call it interstage pressure. Is that right? The IT, is that just
Yeah,
so
it's used. Yeah, it depends, I guess, who you talk to, but
I call it
sometimes I've
parallel
heard it
compression,
referred to.
but some other people will say it's interstage pressure. So really, how does that
Right.
work? So you get pumped into the same gas cooler. What's the benefit of having, say, this parallel compression?
Yeah, great. We go back to Trevor, that bypassing flash gas again.
Yeah.
And if you understand that as a service tech, that inefficiency going from the flash tank to the medium temp suction, I said earlier, it's all about trying to manage that and reduce that. And if you can't reduce it, how do I make the system more efficient? And that's what parallel compression is. So you've got an additional suction group, and that compressor turns on to manage the excess flash gas coming from the flash tank. So my medium temp suction could be running at 425 psig, for example. But my parallel compressor is running at 550 psi. That's 125 psig higher suction. And if any of you have ever looked at a compressor curve, compressor tables, we all know that the higher suction means much more capacity, number one, for that same pump, and much lower energy because my compression ratios are less. That's a second advantage. And the third advantage is my discharge temperatures are lower. So I've got three
Yeah.
benefits there. And you add all those together, that means lower energy. So parallel compressor sitting there, you say, okay, well, when does it turn on? Right? It just doesn't run all the time because in the wintertime, I don't have enough flash gas to feed my parallel compressor. So it's off. So the flash gas coming off my flash tank goes to my bypass valve. And the bypass valve in the winter is just trimming it as it needs to. But as it starts getting warm in the spring, and now I'm starting to increase my pressure in my flash tank, my bypass valve starts to open more and more and more. And the mass flow through that valve at one point will equal the minimum capacity of my compressor, parallel compressor, running at minimum speed. And once we get to that point, what happens is your controls on your system will turn on the parallel compressor at minimum speed and will shift the set point of your bypass valve higher so it doesn't bypass.
Wow.
So now my compressor starts to digest that extra, my parallel compressor starts to digest the excess flash gas. And it's doing it much more efficiently because it's 125 psi higher suction. It's running at 550 instead of 425. Discharge temperatures are lower. Capacities are very good, they're high. So you're discharging now into your gas cooler at a lower temperature. So it's kind of a win-win.
Yeah, so you're saying your compression ratio is lower. What does that do to like the capacity of the other compressors or the size of the other compressor? Does that change how you will design a compressor rack?
Great question. Absolutely, because if you know that you've got X capacity can be handled by the parallel compressor at peak load, that means you don't need as many medium temp compressors. You know, you might have had those 10 before that I talked about. It's a
Yeah.
huge rack, but let's say we had 10 before. You might be able to go to 7. I
Wow.
don't know exactly the
Yeah, yeah.
numbers, but and also don't forget, because you're running at a higher suction, you can actually have smaller capacity compressors, smaller displacement compressors that are giving you equivalent capacities to the bigger ones because you're running at a higher suction,
Yeah,
right?
amazing.
So retailers and designers are now that they got really their arms around that, they're really trying to play around with what is the optimum sizing for those parallel compressors, and how can I get them to run even lower ambient so I can have smaller compressors, medium compressors, maybe even a different sizing of those parallel compressors to have them run as long as possible, to save as much as possible, to make the entire system more efficient year round.
So on those parallel compressors, I'm assuming there would be drives on those ones as well, and there could be multiple ones, I would guess, sometime.
Absolutely. So your lead compressor will have a drive on it, like your medium temp. So you are adding some system complexity when you do that, because now you've got a medium temp suction group with a drive and a medium, on the medium temp suction group. And then if you're adding more than one compressor, then of course, or even if you have one or two, you'll need a drive on the lead.
Yeah. And
If
so
you
then,
want smooth modulation, of course.
yeah, because that comes in, like you said, more complexity compared to just say that adiabatic cooling. But now we're adding complexity that you're going to gain a lot of advantages of for all the other compressors, as well as the design of the rack. And
Sure.
have you been seeing any of that implementation in like Canada as well, like going to parallel compression or these cooler climates, or is it still more of the booster type system or the basic?
No, it's starting to find their way on systems more and more, and we're talking to OEMs and end users that are starting to specify that in their base spec. So it's gaining some popularity, that's for
Eh,
sure.
Excellent. And when you talk about it too, because I really always want to think myself personally of the technicians and on the things that they will need to do. And I say this in all my trainings that with any new technology coming out in refrigeration, it doesn't matter if it's CO2 and if it's VRV or VRF or heat pumps, it's all about the controls.
Right.
You need to understand the controls. And so these new strategies, even that bad adiabatic one, there's a strategy on the control side. And like you said, it hits 72, you got to open the solenoid valve. So we really need to think as technicians how to control this stuff and really take the time to learn controls, because going forward in the future, all these newer systems, and it doesn't matter if it's CO2 or A2Ls, you're gonna need to understand control. So take the time to learn that stuff. So that's an interesting technology, parallel compression. So
Yeah, that's a great point about the controls, Trevor, because and I'm sure you've talked to service techs that have worked on CO2 systems as well as HFC systems. The guys have done a lot of CO2 work. You ask them, what systems would you prefer to work on? They'll all tell you CO2, because these guys are techies. They love controls. They can troubleshoot it from their dinner table and understand whether they need to come in, because all your expansion valves, you can dial into them because they're all electronic, whether they're pulse or stepper, it doesn't matter. Your high pressure valves, your bypass valves, everything it's got pressure transducers and temperature sensors. So you're
yeah,
absolutely right.
yeah, no, and that's great. So we talked about adiabatic, we talked about parallel compression. What's another one that we really need to understand and know that's out there?
There's gas ejectors as well, which kind of dovetails into parallel compression. So gas ejectors is a high ambient strategy. Now you may have heard of gas ejectors and then liquid ejectors. Liquid ejectors, we could talk later, but that's not a high ambient strategy. It's an annual strategy. It doesn't matter. It's not affected by ambient. But a vapor ejector, again, is a way of managing the that bypass gas again. And how do you eliminate or reduce those medium temperature compressors from running at a 425-pound suction and shift a lot of that load to the parallel compressors? That's really what ejectors are trying to do. They're pulling suction vapor from the medium temp. They're feeding the flash tank so that excessive flash gas could be managed by the parallel compressors, if you can visualize that. And what it does, it's really a valve, a specialized valve that takes advantage of the high pressure, the motive force, the high pressure coming out of the gas cooler. And I don't know if anybody on the line has ever siphoned a little gasoline because your car ran out or whatever, and you gotta, you create that suction on one side and you're pulling it in. But that's really, an ejector is taking the high pressure from the discharge. It's got a connection that's got suction medium temp connection. And now that high pressure is creating a vacuum effect through a venturi that draws suction vapor away from the medium temperature compressors and deposits it in the flash tank. Now, of course, you can imagine that's creating more gas in the flash tank. Well, the parallel compressors are there to get rid of that excessive flash gas. So really, ejectors are feeding the parallel compressors so that the medium temp compressors can work even less at that low suction pressure.
Ah, so that makes sense now. So this technology you do need to have with parallel compression. So like adiabatic, you don't need parallel compression, but it's probably beneficial if you had it. But
Right.
okay, so this vapor ejector, you need it with parallel compression. Okay.
And there are certain criteria and points of pressure, but you need enough motive force and enough volume in order to draw it over. So that needs to be in place, but that's really the impact. Now, if you, for example, we talked about in a high ambient area that the water is either not available or so bloody expensive that someone doesn't want to go adiabatic gas cooler, well, a gas ejector is a great option because it's managing those high ambient periods of time by trying to shut those medium temp compressors down as much as possible and transfer all that vapor to a more efficient parallel compressor operating at a higher suction pressure.
Yeah, that totally makes sense. And it, like you said, you don't think about these things like, oh, well, do we have water or not? You know what I mean? But if you don't have access to water or if it's super expensive, this could be one of those solutions that help. So this is why you need to understand this stuff and take the time to do your research on the different technologies. So
Yeah,
you
no,
all
it's
go ahead.
sorry, go ahead.
You also said that there's vapor or liquid ejectors. You want to just
Right.
elaborate on those a little bit?
Yeah, liquid ejector is a technology that runs year round. There's other manufacturers out there that have these low superheat technology. And what liquid ejectors and low superheat patents and technologies have out there that manufacturers have developed is revolves around running your medium temp cases at just about zero superheat. Okay.
Wow.
So if you can run your medium temp case at a zero superheat, you can run a little bit higher suction because you don't have to worry about that extra superheat range and pressure drop within your evaporator. If you can run at zero and you can float up a couple of pounds, again, a couple of pounds on a million BTUs or 700,000 BTUs, that means your compressors are going to be much more efficient. So compression ratio will be reduced, energy will be reduced, and discharge temperature will be reduced. But that's an annual thing. So here's the problem with zero superheat. You've got zero superheat. And
Yeah.
so our compressors don't like zero superheat. So the systems have been designed with a special accumulator, a low pressure tank or suction accumulator, however you want to call it. And the liquid ejector basically has the same concept as a vapor ejector. So it's literally drawing by using the high pressure from the gas cooler. It's siphoning liquid from that suction accumulator, returning it to the flash tank to be managed by the parallel compressor. Now, other designs are out there where they also have means of managing that liquid. Some manufacturers will take that liquid, bring it to an accumulator, and then feed the low temperature cases with that lower temperature, high enthalpy rich liquid.
Wow.
So they're not wasting it. So depending on the manufacturer, there's different patents around out there, but that's an annual way to save energy, and it's unaffected by your ambient temperature.
Wow. Yeah, that's very interesting. Where, you once again, we don't talk about, okay, 0 degrees superheat the case. That is a no-no in refrigeration. And now
Yeah,
we're getting into technology where we're using that to the advantage of it having, less of a compression ratio, higher suction pressure to get to maintain that same temperature. So that is
right.
super cool. I can't wait to see that in the field myself personally. That'll be nice.
A lot has to do with the efficiency of those refrigerated display cases. So if you've got in North America here, the DOE has really high efficiency levels for refrigeration display cases. So there's not a lot of floating capability. There's some about 3 psi, 3 or so psi you can float up. But in other parts of the country, it could be 5, 6, 7 psi float.
Wow.
So depending on where you are in the world and what case designs are out there, you can have a much greater impact on that.
Yeah. And even what you said, the design about using that already cold liquid
Right.
for that low temp, like that's just a great, like just thinking about it for me, myself personally, haven't heard of that one, but just thinking about you having now nice, cold, quality liquid already done, not having to use a subcooler, not having to use mechanical means, it is done already and you can use that to an advantage.
Sure, you got 20-degree liquid coming off those medium temp cases, and you're repurposing it as long as you've got enough liquid to feed the cases, and all that's calculated and controlled within the controllers on when to open and when to close. So yeah, that's definitely a strategy that's out there.
That is awesome. So, is there any other warm ambient strategy that could be used or implemented in CO2?
Sure, sure. There's mechanical subcooling too. And mechanical, I know we've had conversations around that before you left Emerson around mechanical subcooling. It's another means. Typically, it's putting a heat exchanger at the outlet of your gas cooler. Now, typically that'll be a separate unit. It could be a small propane unit, but most often today it's an HFC unit. So until anyway, that is a means. So when you're in areas where you've got extremely high ambience, it's a great way. And I think, well, I know that when you're above 87.8 degrees and you're in supercritical mode or transcritical mode, pressure temperature relationship no longer works, right? And that's one of the things about a CO2 system that designers, OEMs take advantage of, because we can actually, when you're above the critical point, we play around with the optimal discharge pressure to make it the most efficient, regardless of what the temperature is. So at every gas cooler outlet temperature, there's an optimal pressure that we're controlling to. Okay. So what I'm trying to say here is that even though your pressure may be high or your temperature may be high, when that hot temperature leaving the gas cooler enters this heat exchanger, even though it doesn't drop the pressure, it does lower its temperature. Okay. And when your vision an enthalpy diagram, and one thing about a CO2 system is when it hits that high pressure valve and it drops, it creates flash gas. Well, the mechanical subcooler moves the line over to the left of the chart, so it will create less flash gas. Yes, it'll still be at a high pressure, but the flash gas it creates going into the flash tank is reduced. That means you don't have as much flash gas bypassing to the compressor, medium temp compressors, thereby adding efficiency and increasing the EER.
That's very interesting. So we're not changing the pressure, but we are changing the temperature of the gas, and it reduces that bypass gas, that flash gas.
Right.
That's amazing.
Same thing like an HFC system. When you subcool your liquid, And you say, okay, my liquid enthalpy is so high going to my expansion valve that my expansion valve doesn't need to create as much flash gas to go from 50-degree liquid to plus 20-degree vapor. I don't have to create as much flash gas. I don't have to transfer as much energy to get me down to that point, because that's what an expansion valve does, right? It just transfers energy, and it needs flash gas, that energy released through the flash gas, to drop its temperature. So we're doing less of that when your liquid is colder going into it.
Wow, that is amazing and interesting. Is there any time where you would use all of these technologies, or would you? We already talked to you. Could use adiabatic and parallel compression. You could use gas ejectors and parallel compression. Is there any? Would anybody ever design a system with all of these technologies, or would it not be cost or feasible, or not make
For the
sense? I
most,
guess.
well, it's all about the capex and the complexity as well. It's possible that in a certain extreme ambient region, that you may have one high ambient strategy overlaid against the other, because the energy may be so high in that region that it doesn't make, that the capex outweighs the energy penalty. Oftentimes parallel compression and adiabatic can be combined, or ejector, of course, and parallel compression is combined, or you might have a mechanical subcooling added on to an ejector type system or something like that. Some of those combinations, but yeah,
Yeah, that's
they
very
can
interesting.
certainly be in
And so,
combination.
so with these, you talked about earlier about these year efficiency gains on the flooded evaporators. Could they be matched with like really any of the high ambient strategies? Would that be something that we're going to see maybe in the future?
Absolutely, it's independent of the high ambient strategy. Yeah,
Okay,
yeah,
great. I can't wait to see
yeah.
some of those.
Well, another
Before,
thing.
yeah, go ahead.
So go ahead.
Nope.
I was just going to talk about um, the heat reclaim, because it kind of dovetails a little its understanding of heat reclaim for CO2 systems, because we were just talking about this in an article that we're doing, which is kind of interesting because it dovetails a bit with the mechanical subcooling, a similar um, understanding. One thing about CO2 with heat reclaim versus an HFC system, an HFC system, when you're trying to do heat reclaim, you artificially have to keep your head pressures high, right?
Mhm.
And if you keep your head pressures high on an HFC system, your liquid quality is not good, because it's hot. It's hot liquid because you've got saturation that occurs. You got hot liquid goes into a receiver and you feed your expansion valve, and your expansion valves have to create a lot of flash gas, right?
Yeah.
With a CO2 system, what's really interesting is even in the winter, instead of floating the head pressure down, okay, if we need a lot of heat, we'll artificially bump the head pressure just above the critical point. So we can get a lot of heat from our compressors, but it's cold outside. So even though the pressure's high, my gas cooler temperature is low. And what happens to the gas cooler when it's low coming out the temperature? I get less flash gas going into my flash tank. So I can still get lower flash gas in my flash tank while I'm heating hot water very efficiently with CO2. And it's much more efficient than any other forms of hot water heat. So
Yeah,
anyway,
and
just
that
thought I'd throw that in there.
no, I did have a question on that, but good, you answered it already. It's interesting because I did have some friends that I talked to, and when we were going through the training, when I was going through your trainings and the mentorship from you, is that I talked to some of my buddies, and they're like, and I was learning about these strategies. They're like, yeah, my system's in transcritical mode right now, and it's minus 20 out. And that was the exact reason why here we
Sure.
do a lot of that heat reclaim or heat recovery here using these systems, and they're more efficient than HFCs, which is great to know that.
And it's all about, understanding that even though your pressure's high, my temperature coming out that gas cooler is going to be relatively low because it's cold outside. And when it hits the high pressure valve, it does not create as much flash gas. And that's a benefit.
Yeah, that's amazing. Before we get into questions from the participants, what advice would you give to technicians out there first, getting involved with CO2 and CO2 refrigeration? Like, you have any advice for them on things that they should be looking at, things they should be doing, so when they come up to a CO2 system that they're maybe a little bit prepared?
Yeah, that's a great point. When we were doing a lot of the trainings in Brantford and moving around, one thing that I did tell the technicians is, if you don't know much about CO2 today, you should start learning, because it will differentiate you as a service technician from the rest. It'll make you much more valuable to your company and to your customer in the future. And that holds still true today, because CO2 is really at its infancy in North America. And if you want to differentiate yourself, learn it, study it, and work at it, because I know that there's a thirst, there's a really need out there. So to answer your question, the most important thing to me is understanding that, not to get freaked out by the fact that you could have 1,400 pounds of pressure in your discharge gas, because the systems have been totally designed to handle much higher pressures than that for first place. And the other thing you need to understand is that that 1,400 pounds only goes from the discharge of the compressor up to the gas cooler and to the inlet of the high pressure valve. That's where it exists. It's mostly all outside, other than the discharge line going through the roof. So that's one thing to understand. And systems pressure reliefs by code need to be outdoors, except for the compressor one, which is significantly higher than the system pressure relief. So that's one thing. The other thing about a CO2 system that's different from an HFC system as well, and you brought it up, Trevor, is controls, controls, controls. So if you don't know controls, you're going to have a hard time working around a CO2 system. If you're very control savvy, you're going to shine in a CO2 systems if you know the basics of refrigeration and the peculiarities that we just kind of talked about here on CO2. You know the basics, you know the CO2 peculiarities, but you're an expert in controls, man, you're going to shine. And of course, there's other little things, but those are the two main drivers, I suppose, that.
Yeah, and I totally agree with that. Understanding the pressures, a lot of people, that's what they say. It's high pressure. CO2 is high pressures. Well, it is high pressures, but I like the point that you just pointed. Most of that's outside. It's not in the case. It's, you're working on the case or something. It's not in the case. It's, it's from the discharge to that high pressure valve. And to understand that and just wrap your head around that, it's been around. CO2 has been around for over 100 years. It's not new to the industry. Like,
No.
we're getting more advanced technologies. All the safety's involved now. Like, and we got all the pressure reliefs. Like you're saying, it's it's getting more and more evolved, and which make it easier. Once again, I want to thank you so much, Andre, for taking the time to speak with us all today. If anybody has any questions, you can unmute yourself to ask Andre or myself, or you can throw it in the chat, and we'll stay here for the next couple minutes, if you don't mind, Andre, to answer questions.
Yeah, absolutely.
Yeah, I really think the control side as well, like we talked about, anyone listening out there, you really want to spend the time to learn that control side. Take the time to understand whatever type of controls, whatever manufacturer it is. And I highly recommend learning a couple of them, because in the end, they're going to be working all the same way. They're going to have pressure transducers, temperature probes. They're going to have boards. They're going to have some sort of interface. And you don't have to learn this overnight. Start little by little, 20 minutes a day, 10 minutes a day, until you get it. And you might not be seeing it now, especially if you're in commercial refrigeration. You're going to be seeing it. There's thousands of CO2 heat pumps. There's thousands of supermarket transcritical racks. There's thousands of condensing units out there, I'm sure, with CO2 in it. So it's just time to prepare yourself now, so when you start seeing it in maybe 3 or 4. Some of you are seeing it now. I know a few of you on here are seeing it now, but those that aren't, you will start to see this.
Yep. Absolutely.
So we had one question in the chat here. So typical pressures of the suction and discharge for medium temp and low temp. Yeah, why don't you go over what are typical low temp, like that subcritical pressures you would see in suction and discharge, Andre?
Yeah, so if we take a look at, there's basically 4 pressure zones in the CO2 system. The discharge I talked about can range from 700 to 1400 pounds. That's medium temp discharge. That flash tank or intermediate pressure could be around 550 pounds. So that means your flash tank's 550 pounds, your liquid line's 550 pounds. Then you go to your low temp minus 20 or around 200 PSI. Medium temp, around plus 20 or around 425, something like that. So you got 1400, 550 liquid line, 425 medium temp suction, about 200 pounds low temp suction. So you can see all of those other pressures, except for 550, okay, but 410A at 130 condensing is almost 400 pounds.
Yeah.
So all of those other pressures are kind of like the top end of the 410A pressures.
Yeah, and people are working on that every day. In Scottsdale right now, it's 425 PSI and 410A system.
Right.
I got another question here. What is the COP of CO2 system we get compared to a regular Freon system?
While COPs can vary, of course, depending on the technologies that you have, but they're somewhere in the mid 3 range, typically. That's pretty much the range of them.
Yeah, for sure, because it's going to be different on the technology depending where you're at in the world. It's going to be different here in Canada than if you're in Phoenix, right? Depending on the technologies.
Yeah.
Okay, I don't see any more questions in the chat. If anyone else has any questions, please throw it in. Once again, Andre, thank you so much for this. This has been amazing.
My pleasure.
And if anybody else has any questions, you can either, if anybody needs to get a hold of you or Emerson and want to find out more about Emerson Solutions, how would they do that?
You can email me. You can find me on LinkedIn, or you can email me at my first name, Andre, dot my last name, Patenaude, at emerson.com.
Yeah, it's not hard to find Andre. He's been talking CO2 for a long time. And once again, thank you so much, Andre. Thanks, everyone, for showing up today. And we'll see you at the next CO2 Mondays with Trevor. Have a great day, everyone.
Thanks a lot, Trevor.